Okay. Hi, everyone. Nice to see you again. Today we have the third talk in the colloquium series for this year. And first of all, I would like to acknowledge the traditional owners of Australian land and pay my respects to the elders, past and present, acknowledge the people of the Kulin nations. Today, I'm happy to present Professor Katharina Franke, who is a professor at the Freie Universität at Berlin. She is one of the leaders in the interplay of magnetism and superconductivity, as well as in the molecular electrode junctions. Katharina received her PhD in 2003 at Freie Universität Berlin. After postdoctoral appointments at École Polytechnique Fédérale de Lausanne, she returned to Freie University as a postdoc, and in 2009 became a junior professor and later a full professor. Katharina has been awarded Hertha-Sponser Prize by the German Physical Society and European Research Council Consolidator Grant. Okay, Katharina, the stage is yours, and we will enjoy the talk.
Well, thank you very much, Dimitri, for the kind introduction, and first of all, also for inviting me to give this online talk. Yeah, as Dimitri mentioned already, I would like to speak about magnetic atoms and superconductivity and this interplay. And you can also already see that this is on the single atom scale, which we want to investigate. So therefore, we need a scanning tunneling microscope. But before I get started, I really want to thank the people who did the work. Without them, it would not have been possible. And this is my group, but in collaboration also with theory. But for my group, I would really like to point out Eva Liebhaber, Martina Trams, and Lisa Rütten. So these are the ones who did most of the work that I'm showing here today in the lab. And then we also have a very fruitful collaboration with Felix von Oppen, who is also in our department here as a theory, and his PhD students, Harald Schmidt, Larissa Melischek, and Jakob Steiner. And you will see that one of the superconductors I would like to discuss, they come from Kai Rossnagel in Kiel, this niobium diselenite. Okay, so superconductivity was one of the keywords in the slide, and obviously you know what a superconductor is, and well, its most prominent signature is, of course, that when you cool the material down below a critical temperature, then the resistance drops to zero. And another property that is important for us also today is, of course, that it's a perfect diamagnet, this superconductor. So how you can actually notice is that a superconductor or a magnet would be floating on top of a superconductor because the superconductor expels all these magnetic field lines, and therefore this leads to these nice figures that you typically see. And another important ingredient is, of course, so we have basically the control of temperature of magnetic field to essentially also destroy superconductivity if you come from the superconducting state. But on the other hand, if you have a superconducting junction, there's also, I mean, your phase diagram, so it's limited. So if this is the superconducting region, it's limited by a critical magnetic field, it's limited by a critical temperature, but it's also limited by a critical current density that you can put through. So therefore, you get only this small or this area of a superconducting phase. And you see now that maybe also this critical current or the current that you push through a junction may be one control parameter, and this will come important for some part of my talk. And the other part is that you could ask yourself, like fundamentally, I mean, okay, this is a macroscopic magnet that's floating on top of the superconductor, but what about the tiniest magnet that you can think of? And the tiniest magnet, of course, is a single atom. Okay, but how should we treat a single magnetic atom? I mean, you also know all about magnetism. We know what magnetism is macroscopically about, but we want to go to the atomic scale. And so essentially what you could say, like, okay, then your smallest magnetic moment could be a classical magnetic atom. So you have some unpaired electron spins that give it a momentum. But okay, if you think about it, it's a very small scale, of course, it's a single atom, and in many cases, the quantum properties of this atom become important, and in particular, when you put a magnetic atom on top of a surface. So, I mean, this gives rise to, I would say, new physics or rich physics phenomena. Of course, they by now are very well known due to this exchange scattering with substrate electrons. Well, and as I said at the beginning, if we want to look at single atoms, I mean, the tool of choice is probably a scanning tunneling microscope. So I guess I don't have to introduce it here. So basically what we will do is we locate single magnetic atoms that we have deposited in ultra high vacuum on the surface. And but apart from, you know, imaging the surface and doing spectroscopy that are kind of the common modes of operation, I will also show you that if you take a superconducting tip and a superconducting substrate, of course, you can approach the tip very close to the surface, and then you get these Josephson junctions. And that's one part of the talk that I would like to address later. So our working environment is ultra high vacuum, and it's also, of course, low temperatures, and roughly it's 1.3 Kelvin of the data that I want to show today. Okay, so single magnetic atoms on superconductors are actually already well known, and I just mentioned briefly before that in general, single magnetic atoms on surfaces, you want to explore the physics of the exchange scattering. But interestingly, I would really like to say that the first single atom signature on a surface were indeed the ones of a magnetic atom on a superconductor. So this is the paper back in 1997 by Ali Yazdani, where if you compare, they did spectroscopy on top of locating the tip on top of these atoms, and then they found here the superconducting energy gap, but compared to just a bare spectrum on the surface, then you see that there's a slight asymmetry. So the energy resolution isn't very good. I mean, at that point they measured at 4 Kelvin and they used metallic tips, but still you could already identify these so-called Yu-Shiba-Rusinov states. Almost at the same time, you didn't necessarily have to put the magnetic atoms on top of a superconductor, but also on a metal. And they're kind of at the same time, 1998. So there are these two very nice papers that have seen that there's something going on at the Fermi level as well. And this has been ascribed to a Kondo resonance. And that's, of course, also due to exchange scattering of this magnetic moment with the now itinerant electrons of this metal. And just a few years later, then Andreas Heinrich, back then in the Eigler lab, he discovered that, okay, if you have a single magnetic atom now slightly decoupled from the substrate so that you suppress a little bit this exchange coupling, but you have a thin insulating layer on top, then this atom behaves differently. So if you switch on a magnetic field, you see that there are steps symmetric in bias voltage around the Fermi level. Oops, here, so this is the Fermi level. I cut it out apparently. And these are so-called spin excitations. So this is very different in the sense that, okay, so you are almost a free atom and you can change kind of the spin projection of your magnetic moment. And obviously this is kind of the Zeeman effect on the single atom scale. Okay, but as I said, I would like to discuss what happens to magnetic atoms on superconductors, so much more of this type. And I would like to get a few words now also on these Yu-Shiba-Rusinov states. So as I said, I mean, here you see a slight asymmetry, but what does it mean? So already at that time, they interpreted it very well and nicely that, okay, so there need to be states inside of a superconducting energy gap. So we are dealing with a BCS type superconductor, which means, okay, you have your depletion of density of states around the Fermi level. And obviously this energy scale is given by the superconducting order parameter. Now, if you have magnetic exchange scattering to an impurity, back already in the 1960s, Yu-Shiba-Rusinov independently derived that there should be some states inside of this superconducting energy gap. And the energy that you find where these states are, they precisely scale with the exchange coupling strength that's given here by the J. They also should scale with the spin of the adatom, and with nu naught, that's the density of states in the normal state of the material. And so this parameter is the most important one, but there's an additional one that is the potential scattering. Of course, I mean, you put an atom on the surface, you have a different chemical potential and so on. So this is also potential scattering, and here this is what is called K. And this is also a small correction to the energy, but where it will become important, most pronounced, is that you, in contrast, so the superconductor always has particle-hole symmetry, but now by this potential scattering, you slightly disturb it, and therefore you get these states at different weights inside of the superconducting energy gap. So important to note, there's exchange coupling, there's potential scattering, you get the states, and also let me put it in a very simple picture, I mean, you have your magnetic atom on top of a superconductor, you have the exchange, the Cooper pairs, and let's say if there's an exchange scattering, I mean, you kind of, let's say it's antiferromagnetic, then one of the spins of the Cooper pairs in a very simple picture would be kind of attracted, the other one repelled, and therefore you get states inside of the gap, because now an excitation is much easier. Because here, this is one important thing I would like to note. I mean, we are doing a tunneling experiment, so we have a tip, finally, that's on top of the surface. So what you would like to do is you want to inject an electron or a hole into the superconductor. So you have to find here a way to do that. And I mean, either you have to break the Cooper pairs, that's why you have to go beyond the superconducting order parameter, then you can tunnel in. Or now, if you have these bound states, basically this already happens at lower energies. And well, the easy picture that I try to draw is like, okay, yeah, now because you kind of locally perturb your superconducting condensate, it's easier to do that, so you get it at lower energies. Okay, so another feature of these states is that, okay, you think about it, I mean, they are really in a very nice gap. I mean, it's a tiny gap, but it's a perfect gap. So basically, in that sense, you could say that, I mean, okay, you have this exchange interaction, but then from further interactions, you could also say in simple words that then they are kind of protected to have it from the, the bulk high energy states. These are kind of far away, and it's protected from the interaction with these electrons. And this is nice, because imagine that if you have these states, now this would be, let's say, a single magnetic atom, like pictorially saying, okay, you have this pair of Yu-Shiba-Rusinov states, but imagine that, okay, if you put a second atom next to it. So, I mean, generally people are, of course, interested in what happens with the interaction with these atoms. And now if you have these states that you can really resolve very well, you can easily, or, well, whatever is easy, but you can see interactions, and for instance, then you could see an energy splitting if you have hybridization. So there have been theoretical predictions already years back. Actually, I should mention that already in the first Rusinov paper, that he mentioned that there should be this hybridization, but then, of course, many more theory papers came up. So this splitting is something that you may expect. And now, of course, there's the thing that, okay, one too many, so you should have hybridization. Eventually, you should have band formation, and so potentially these bands could form, so Yu-Shiba-Rusinov bands inside of the gap. And well, what is now very interesting is also that, okay, imagine that these bands they cross the Fermi level and not stay, as I was kind of sketching them before, but if they overlap and cross the Fermi level, then there are theoretical predictions that, yes, you should have an opening of a topological gap. And potentially then you should also have these Majorana end states at the very end of the chain. And this is, of course, a very interesting topic of research. So there have been many publications, so I wouldn't be able to finish this list here, that both experimentally, but also, of course, theoretically have investigated it, and in particular the phase diagram and so on. So I have to say today my main topic is not this, but this is a very, very interesting one. And I think that other groups are actually even more in deep into it to, let's say, look at also the atom assembly on that. But I will show you an example where we also build a chain.
Could I interrupt you?
Sure.
Is this, you mentioned this asymmetry introduced by this B factor. Is it small or is no? Are these peaks dark blue and light blue are comparable, or one could get that, I know, one is much larger than another one?
Yes, you could actually get one much larger than the other one, so that sometimes one should be really careful that you not overlook one, which is very small at one bias voltage, but at the opposite bias voltage, you would immediately see that it's there. So yes, they could be very different. And we have a problem to really control that before in the experiment. So it's really like an experimental paradigm. We put different magnetic atoms on the superconductor, and something that comes out and tells us that the asymmetry changes, so that the potential scattering must have changed. But unfortunately, it's not easy to tune, for instance. And so, yeah. And also it could be, I mean, you don't know on which side they are, right? They could be like this or like that in either direction in the asymmetry. And it's, well, difficult to predict. I mean, for me, impossible, but yeah. Good. But you can get basically any asymmetry that you want.
May I also ask a question?
Sure.
this is about this Yazdani data which you show, right, in 1997. Because looking at your picture, theoretical picture, and looking at the resolution, I would say that naively, if there are two delta functions, I would expect not just asymmetry. I would expect a clear signature of peaks, with some broadening, of course.
Yes. Well,
so to me, this plot is not convincing at all. I would say it's normal Coulomb interaction, catalyzed by manganese.
Yes. Okay. So, I mean, looking backwards, I can say that I really very much trust this data. But I agree, like, if you first look into it, it could be many, many different things. And to put it down, what I didn't show here, and I don't have the graph here, they also show a distance dependent and an oscillation dependence, which fits into that you have these Yu-Shiba-Rusinov wave functions and how they should decay with distance. So I didn't mention it here. I think that this is another good indication that you have this oscillation. Yes, of course, but let me show you actually some data that is very similar. So it's manganese atoms on lead, and there you see really the peaks nicely resolved now at lower temperatures and using superconducting tips. That will be spectra I will be showing in the following. And if you would take these and put a lot of broadening, you would end up with this spectrum. So I would say it was correct, the interpretation, even though they did have but obviously, I mean, now it's almost 30 years back. So for that, I still find it impressive.
Okay, thank you.
Okay, let me go here. So yeah, so I would like actually to convince you that there are states that you can resolve, because I also just made my point that yes, they should be nicely resolvable, and then you can learn about more physics about interaction. So I would like to introduce you some iron atoms on niobium diselenide, how they interact if you have two of them close to each other. And with the manipulation capabilities of the STM, you can kind of build any structure that you like, depending on the adatom and substrate interaction that you have. And then I would like to show some chains, but already with the asset that we didn't find here, Majorana states, but still there's interesting physics going on in the chain that I would like to show you. And then finally, I would like to show, I mean, usually it's all about this exchange coupling strengths and what happens to these states in the gap and hybridization and so on, but also that this asymmetry may be crucial, and that where we find it in one of these Josephson junctions, so where we really approach the STM tip toward the atom. Okay, let me start. So which system do we take? So those of you who are familiar with niobium diselenide, you know it already because you've seen the STM image in the charge density wave before. Okay, so why niobium diselenide? So this is a superconductor that has a critical temperature that we can easily access. So it's 7 Kelvin, and our measurements are at roughly 1 Kelvin. So that's good, of course. But the other important feature that we would like to make use of is that it's a quasi-two-dimensional superconductor. So this is this van der Waals material. You have these niobium diselenide layers. So niobium stacked between the selenium, and then these layers stacked. And then kind of within the plane, it's quasi two-dimensional. And it has been shown by the Paris group that they found iron impurities that were embedded in the bulk of this niobium diselenide material. And here you see that they found Yu-Shiba-Rusinov states. So here's the superconducting energy gap. So here you see already there's better energy resolution because they measure it at lower temperatures. And now, I mean, these are peaks that now are much better than on the slide that we have just previously discussed. You see these separated peaks, still they are rather broad. But if you map them out, you can see that you get this oscillating pattern. So you see what should happen is that you have this oscillation with the Fermi wavelength, and also it should certainly decay eventually. And they have found that this decay is very long range with 1 over the distance, square root of the distance. And this 1 over square root of the distance is an important asset of a quasi-two-dimensional superconductor, while it should be 1 over the distance for a bulk-like superconductor. So in that sense, you see that the extent of these Yu-Shiba-Rusinov states is comparably longer range than on the bulk superconductor. And then the Liljeroth group also made use of that well, if these states, they have long range, then if you put two impurities close to each other within this decay length, then they found that there is already some change in the gap. So there is interaction. So you see this is a single, it's molecules that they deposited on top, but then you see already that there's something happening with the states, and this is hybridization. Okay, so here you see already the superconducting gap of the niobium diselenide. We also measure this, and one thing here you see one spectrum. It's measured on niobium diselenide, so the differential conductance. But I should tell you that in order to increase the energy resolution even more, what we do is we use a superconducting tip. So it could be, for instance, a niobium tip that we prepared on a different crystal. And then because you have also a superconducting tip, you have also a superconducting density of states at the tip, you have these sharp BCS-like singularities. And basically then you measure something sharp and you increase your energy resolution effectively beyond what you should expect from your Fermi-Dirac broadening, so from your temperature broadening. And then you see that it's not just a simple BCS-like superconductor, but you see that the niobium diselenide has here this weird gap structure. And this has been discussed as, okay, I mean, niobium diselenide has a very complicated band structure. So it's particularly at the Fermi level, you have many bands, and so it has been interpreted either as multi-band or a very highly anisotropic superconductor. This is not so important for the rest of the talk, just that we always have comparison and that you're not surprised that this may look like, okay, there's already a state in the gap. No, this is the bare substrate. Okay, so, well, and also another important feature of this niobium diselenide is, so here I show just an STM image, atomically resolved. So the small corrugation is, of course, the single atoms of the terminating selenium layer. But you also see that there's a variation of the intensity. So for instance, here you see these atoms, there's basically a triangular shape. While here on the other side, you see that there's maximum intensity, let's say really on the center of one particular atom. And so this what you see, this corrugation modulation is the fingerprint of a charge density wave that's also there at low temperatures, which is incommensurate. It's roughly 3 by 3 atoms, but not precisely. And this makes you that this pattern that you see actually varies, but there's a smooth transition between the different regions of this charge density wave. And this will be important for us because, I mean, imagine that now you want to deposit atoms on top of the structure. Usually they would like to fall into hollow sides of the selenium layer. So if you look from the top, so this is the atomic structure that you expect. So the yellow ones are the selenium atoms. And then kind of in the layer below, there's either a niobium atom or none. But then let's say we put an iron atom on top. I mean, it either wants to lie here or it wants to lie here because that's in a hollow side of the selenium lattice. But now these sites, if I overlay the same atomic lattice on the two parts of this charge density wave, so here these two areas are cut out. I mean, once this means that you're really sitting kind of on the maximum of the charge density wave if you put your atom here in this hollow site, while if you had this atomically the same adsorption site on the terminating layer here, it would be close to one of these maxima. So therefore, also, I mean, not only the atomic, or I will show that not only the atomic structure is important for these Yu-Shiba-Rusinov states, but also the charge density wave is something that we should not just neglect. For instance, here I show one example. So let's imagine that we take atoms. So here I just indicate them by a cross. They are not there, but I want to indicate where an iron atom is sitting. So we deposited them at low temperature. And so for instance, an atom that would be sitting here on the maximum of a charge density wave, it would show this blue spectrum. Okay, let me maybe go back one step. So here we measure the differential conductance. In gray, I plot this bare superconducting spectrum. Now, due to the scale, you've maybe recognized this double peak feature as a feature of the superconducting energy gap of niobium. The gray back area is just the gap of the tip. And then, but within the gap of the niobium diselenide, you see that on the blue spectrum, you see clearly these two states. And there's also another modulation that's different to the bare superconducting background. But if you put an atom that's, let's say, close to the charge density maximum, the spectrum already looks very different. So the energy of these states, let's say, so there are also peaks, is very different, but also these intensities. So in conclusion that we could draw here, and I don't want to go into the details very much, is that yes, these Yu-Shiba-Rusinov states, they also depend on the charge density wave. And that's, if you remember, in our equation for the Yu-Shiba-Rusinov states, there was still this normal density of states in there that affected where these states are. And this is precisely what we see here. So we could actually do a detailed study on that, but that's what I would like to not show in detail here. What is important is that, okay, if we know that the charge density wave is something that plays a role, then we should probably make sure that whenever we want to look at atoms, they should be in equivalent adsorption sites. So not only that they should be on hollow sites of the selenium lattice, but also they should be on the same sites with respect to the charge density wave. So for instance, then the closest distance that we could have between atoms in equivalent sites is, let's say, an atom on this part where the charge density wave maximum is, and another one which is here. And that's then 3 atomic distances apart. And obviously, due to this 2-dimensional nature that we have in niobium diselenide that we were aiming for, these 2 atoms should still be seeing each other and interact with each other. Okay, obviously, if you put atoms just by chance.
Could I interrupt you?
Sure.
If you have this profile, does it mean that atom has, you know, some energy profile, and there are some preferable spots where they want to sit and they're trying to get there? Or if you place it, it will be there for forever?
No. So basically, so when you put them, just, you know, I don't have an overview image here. So these atoms usually, so we deposit them at low temperature, and what we do find is that they are always sitting, when we can really get nice resolution of the selenium lattice, that they are on hollow sites.
I see.
So that's kind of the energetic minimum, and I mean the deposition is, let's say, at 10 Kelvin roughly. So okay, they fall somewhere by chance, but apparently they always have sufficient energy to get into this potential minimum, let's say, of the atomic lattice. But then they are weakly bound, because then, which is good for us, because then, I mean, they are sitting somewhere, but then we can manipulate them with the STM tip. Because otherwise they would be sitting somewhere, and I mean, bad luck for where they are, and you would have to look whether you find some of them which are at sufficiently close distance. But here you see that, I mean, that would be a lot of work. It's possible, but then you can at most see 2 and not 3 and not these long chains. So the idea is that now you take your STM tip and then you push the atoms around. And that's possible because the interaction is still rather weak. So it's a van der Waals material, and you have this, let's say, the iron atom, and then you can move it around.
Thank you.
Yes, thank you. So actually, this was the perfect question to actually get to my point now here as well, that we can manipulate them on this particular surface. So let's say, for instance, the early papers for magnetic atoms on lead. I mean, lead is one of these superconductors where it's highly corrugated and very soft, so you cannot manipulate the atoms. And then other groups, in particular the Wiesendanger group, they looked for other superconductors where you can manipulate, but they had then found superconductors like rhenium, which are very low temperature, critical temperatures. So at 1 Kelvin, we wouldn't be able to measure anything there. So that's why we took then this niobium diselenide, also motivated, of course, by the results of the French group. Okay, so then we place atoms, and now you can see we can build structures, and eventually, of course, we can build structures as long as we wish, or as long as the patience of the PhD student. So that's holds and before the tip crashes. So this is up to 51 atoms that I would like to show. Okay, but okay, here I just sketched the atoms where they are. So I just take this as an indicator. Obviously, the atom is not there, but I mean, here, for instance, you see an image where now the atom is really there, and it looks like, okay, you have this protrusion, and it looks slightly triangular, like due to this interaction with the substrate. Okay, so I was telling you before already that there were these Yu-Shiba-Rusinov states. So actually, one of these spectra I was already showing you. I mentioned that there are these 2 tiny states that are inside of the superconducting energy gap. For reference, again, in gray is the bare substrate. And then you see additionally on top, where otherwise there shouldn't be anything, on the magnetic atom, or at least close by, you see additional states, these Yu-Shiba-Rusinov states. So they are symmetric in energy, but asymmetric in intensity when you look carefully. Okay, this is one spectrum that's taken just on top of the atom. But I think I would like to highlight that, okay, you can measure spatially resolved. So here, the STM image is just in the middle, where anyway, in the energy scale, so this is the same energy scale above and below. But now below, we plot like all the spectra in a kind of false color plot that go along this line. So which means that the blue spectrum is just this blue dashed line, and where you see that there's this small intensity. But you also notice that maybe this was not such a good choice. I mean, the intensity is much larger than when you go slightly off of this atom. Here you see that the intensity of these two states is much larger. So you see that there's a spatial intensity modulation, but if you now take these lines, it's also much more easy to identify these states, and they're really nicely there. And you also see that there's an oscillating pattern. And this is, if you remember that I was showing you this image from the buried iron atoms, that you had these oscillations with the Fermi wavelengths, the same holds here too. Okay, so this is a single atom. Good, we placed it there. Now let's put a second atom, and as I said, we want to have it in equivalent adsorption sites, so 3 lattice distances apart. Then the STM image looks like here in this inset. So there are now these 2 atoms. Now we again take spectra. Let's say first we try to measure just on the center of the 2 individual atoms. So this is blue and red here in the spectra. And well, they are very different than from the single atom, right? So you see at first glance, I mean, there are many more peaks. Okay, so this is one important feature. And now let me zoom in. So here you see, so this is on the center of the individual atoms, and also the 2 atoms are equivalent. But now if we look carefully, so I zoom in into this region. So here, a single atom only showed in this region 2 states. We label them alpha and beta. But in an equivalent energy range, what you now see is that, well, the states have doubled actually. So here, a zoom in into this area shows you that, well, here, this is just the voltage range. The color is again the intensity. So you find that there's a spatially dependent intensity variation, but any state that we previously called alpha now seems to be split, and beta also seems to be split in energy. And importantly, so let me illustrate this at the example of the beta state. So there's one state, so this is through the 2 atoms, and one of the states has a nodal plane, while the other one actually has a maximum intensity just between the atoms. And that's important because, I mean, if you think just in a simple picture, I mean, now you have these Yu-Shiba-Rusinov states. They are any kind of wave function that you can think of. So you have some, you know, like distribution. And if you put 2 of them together, I mean, then you can have the linear combination of these Yu-Shiba-Rusinov states. Either you have a symmetric one where you should get maximum intensity between the atoms, or you get actually the antisymmetric linear combination, and then you should get a nodal plane. And this is precisely what we are seeing here. So this nodal plane and absence of nodal plane kind of already gives a hint that you have hybridization of 2 states. You know, like in a hydrogen molecule, you start with 2 hydrogen, let's say S-wave type of orbitals. You do the linear combination, you get one with maximum intensity, one between the 2 atoms, one with a nodal plane. So this model fits nicely of hybridization of these Yu-Shiba-Rusinov states. And now also here, we really needed this energy resolution to resolve this. Otherwise, there would be just asymmetries beforehand. I mean, you can also say, okay, you should map it out. Here, this gets slightly complicated because the patterns are, I mean, you have here a single atom. We measure now the differential conductance at the energy of this so-called beta state. You see it's varying in space. You may see that there's this oscillatory pattern. And if you put 2 of them together, well, the images get a little bit, yeah, I mean, not a little bit chaotic, but the signatures are clear. So here you see that between these 2 atoms, you have maximum intensity, while here you have a nodal plane. What I showed basically in this plot as well. Okay, so this fits with the picture. Obviously now, every of these Yu-Shiba-Rusinov states should behave the same way. And so maybe here I forgot to mention something. Why do we see many of these Yu-Shiba-Rusinov states? A single spin, so going back to the first equation of Yu-Shiba and Rusinov, a single spin should give you 1 pair of Yu-Shiba-Rusinov states. Now imagine now you have iron, you have several electrons in the D shell, actually, so you have if you have a spin of 2, then you can have 4 unpaired electron spins, and individually they can give rise to these Yu-Shiba-Rusinov states at different energies, because the orbitals hosting the spin are of course different in energy, and therefore the exchange coupling is different, and therefore you get different states. So altogether we actually see 4 states, but I only always point out these 2 because the other ones are already here in the area of the gap. So therefore we always concentrate where we have the best energy resolution, and they are protected the best inside of the superconducting energy. Okay, one thing for maybe, yeah, the interaction is hybridization, but you can have also magnetic interaction. Therefore, we see a change in the energy, but this is maybe a minor detail for today, which is for us a proof. I mean, you can go through this so-called quantum phase transition due to magnetic interactions, but that should not be the main topic today. But if you have questions to that, I would be happy to answer them, of course. Okay, good. So now we understand a single atom gives Yu-Shiba-Rusinov states. 2 atoms, you see hybridization. Now you could ask the question, okay, can you do any other structures? And I would like to just briefly point out one triangular structure, because that is a rather recent result of ours. So Lisa was measuring this, and she considered like, okay, now you have this substrate, and I mean, you have different symmetries, of course, that are available. And before, I mean, let's say if you put an atom here on the charge density wave maximum, you have these 3 mirror axes. And now you have the option to, and what I was showing you before, I mean, the nearest neighbor distance that we can put in order to have it on the same charge density wave maximum is just going 3 atomic sites across this line. But if you were to go into, let's say, this direction, the distance is already larger. But also what is important to us is not only that the distance changes, but if you look at the symmetries, I mean, here you have a mirror plane just, you know, at crossing the connecting axis between the 2 atoms, while in this case, it's just along this dimer axis. And if you think in these orbital shapes of the Yu-Shiba-Rusinov states, maybe you can play now with the symmetries and get also kind of what we call Yu-Shiba-Rusinov molecules with different symmetries. So this is just a reminder. We had these two atoms, and we looked and we saw hybridization. So this number of Yu-Shiba-Rusinov states was increasing, and I also already showed you the image with here we have a nodal plane, and here we don't. Okay, so that was a clear signature of hybridization for us. But now we thought, okay, put the second atom in this distance. And then we also measure spectra. And well, first of all, we were confused. I mean, if you measure on top of these 2 atoms, the spectra are not identical anymore. There's a clear intensity difference in what we see. And this is not just because we didn't hit the atom correctly. Because if you now measure the map, so you map out, let's say, at the deepest energy state, these 2 states, you really see that the symmetry changes. So there's obviously, because there's only the mirror plane that's only along this axis. There's no mirror plane that goes along this axis. So therefore, you now lose this. The atoms are not identical anymore. And so then the question was, okay, maybe this is a detail that we found in the dimers, of course. But I mean, then we thought, okay, maybe we can construct structures to make use of the symmetry. And I mean, we just found it nice that here you actually can induce some kind of chirality in these structures, depending on how you break the symmetries. Here, so you see this opening, let's say, of these Yu-Shiba-Rusinov states, right? And once they turn into this direction, let's say clockwise, and now if you place the triangle just in the opposite direction, then you see that they kind of curl in the other way around. So this is, of course, a signature of chirality. And I mean, these ones, I mean, if you just put like 3 atoms in, you know, like you would like to create a molecule, a planar molecule in gas phase, you would never get these symmetries. You need to have the symmetry breaking of the crystal substrate. And this is something generally in atomic scale engineering. It doesn't have to be on a superconductor where people try to kind of, you know, induce symmetries that were otherwise not present. Okay, so this is just a nice observation that now brings us further to, let's see what we can do again with more Yu-Shiba-Rusinov states and in larger structures. And I would like to just go through, okay, we had discussed already 1 atom and 2 atoms. So just quick reminder, these color plots. So this is our energy axis along the x-axis. I just put in the inset the corresponding STM image. And then we take aligned spectra across the atom or the atoms, and then we see what we get as intensity, right? So here, this was the single atom. These were the two atoms where we already saw an increased number of states. And now we put another atom. So here we have three atoms. And you see that the spectra get more and more busy. So obviously you have an increasing number of hybrid states, right? Because you add another atom, you should also have two states more. So you always increase this number. I mean, we cannot separate them so well anymore in energy because eventually we lose our energy resolution because the states are very close to each other. But what you always see is like, okay, you attach an atom, and it's not like just locally you change the spectrum, but really you change the whole set of spectra along the whole chain. And you basically preserve always a mirror symmetry, you know, like from the chain. So you add an atom, but everything changes, and the chain is still symmetric. And you see that this is delocalized over the whole chain, what you start to get. And I guess that this is something like very reminiscent of band formation, of course. And if you map out one of these states, I mean, they look pretty much delocalized. And I mean, I think that this is what you expect. We increase the number of atoms, and eventually you see that it looks as if the states are kind of, you know, getting to some kind of limiting energy where you get them. But I mean, this is if you have band formation in a very simple picture, right? You start to increase your number of atoms. You have nearest neighbor interactions, but of course also next nearest neighbor interactions. I mean, eventually, obviously, if you put another atom more, if you have already many, you don't change that much anymore. So therefore, the spectra shouldn't change. But additionally, I mean, if you think in band formation that you should eventually have, so here, now this is K-resolved, this is energy. So here we have the quasi-particle continuum on the bottom and the top for the superconducting energy gap. This is the gap. We have here our states inside. So if you get these states of these maps, obviously at some point you should have these Van Hoff singularities, and this is what you can measure the most pronounced in an STM. So therefore, of course, also this doesn't change much anymore once you start to increase the number of atoms. Now, I was saying in the very beginning, this may be an interesting thing to look at. You have these bands, they are crossing the Fermi level, and there had been these theoretical predictions that, well, if these bands cross, then you can, in principle, get topological superconductivity. And we are in the condition. So these bands, they cross. But do we get a topological gap? No, we didn't find any signature of this gap opening. And I mean, if you don't find any signature of the gap opening, we also don't find any Majorana states. So we did not find anything that was at the very end of the chain. And you could say, okay, maybe, well, if you only went to like 10, 11, 12 atoms, maybe that's just too short of a chain. But we went on. And so this is the largest chain that we measured. It's 51 atoms. And again, there we also didn't find any signatures of that. You could argue that, okay, let me just put now spectra again along this chain. Now the energy axis is here perpendicular on the y-axis, but again, this color plot that I was showing before. So in the middle is just the superconducting energy gap of the tip. So if we look for zero energy excitations, this should be precisely at this energy, if you want to find a Majorana at the very chain end. But what you see is, I mean, you see these band formations. So this is the part that I was showing you before. So we have these Van Hoff singularities that we get. Eventually, there's something happening to these bands. So here you see that there's seems to be some crossing, and then you have different bands. And we can explain that as well. So if we kind of, you know, take a Fourier transform, a Fourier filter, take out the atomic corrugation, and we just end up with the charge density wave corrugation, then you see that essentially here we started to place atoms on top of the charge density wave maxima. So that's where we started building. But eventually, because of this incommensurate nature, you can't do this forever, right? I mean, eventually you would get to these regions where you're not in the charge density wave maximum anymore, but you end up on the minimum. And then all these Yu-Shiba-Rusinov states for single atoms were different, and that also happens for the bands to be different. So therefore, but there may be an interesting part of having this you know, this region where you actually go from the maximum to the minimum, and so you have bands at boundaries, and this is maybe something that would be interesting to look at.
Could I interrupt you?
Sure.
The arguments were that when coupling becomes larger, in these cases, electron-like and hole-like bands will start to tend towards each other, then have some topological transition and reopen. But it looks like there is no any trend for electron and hole bands to go towards each other. So is it surprising? They look, I know, very well separated always. They don't.
Yeah, I think this is. I would like to convince you that they actually do go through the Fermi level. Let me see. So this is really something to look at much more closely when you. So we were trying to follow what happens to the individual states. So okay, you start off like you said with the electron-like and the hole-like, and then we really tried to also see what these energies do. So let's say the alpha state that's lowest inside the gap is the most interesting one, because that comes closest to the Fermi level. And we did see, we tried to follow the shape of these, and we actually see that if you go to 2 atoms, the hybridization is such that, okay, so you have like these 2 states, positive and negative before. Now you have hybridization, and instead of having hybridization like this, they already have changed the sides. You can't see it here. So we did do that by looking at the. Okay, let me go back. I think it's very hard to, if you don't stare at it forever. It's exactly here what I wanted to just briefly mention, but so thanks for the question. So we have these characteristic shapes, and eventually we saw this shape. They look different at positive and negative bias when you look, for instance, at a single atom. And if you go through the 2 atoms, so here, this shape that we find at positive bias, we actually now see at negative bias, which means that this has caused the quantum phase transition. So it actually did go through the Fermi level.
I see. So it means that the hopping energy is supposed to be comparable with the gap.
Right. Right. And then you see this, and so then also you increase your number of states, and then obviously you get bands. So then the bands do cross the Fermi level. It's very hard. I mean, it requires staring at these images to be really sure that it has crossed. And then from that on, we go with the 3 atoms.
Imagine that you place them at slightly larger distance that they have. In this case, you will have this hybridization smaller, and you might, I don't know, catch a moment when this topological transition happens. So if distance is larger than some critical value, they don't cross Fermi level.
Right.
But if it's smaller, then they would cross.
Yes, completely correct. And unfortunately, our system is not the one that is the best suited, because, for instance, here you see, we were kind of limited to have it at this 3 atom distance because we want to be at the charge density wave maxima. So you cannot really choose now 2 distances or 4 distances, because then these Yu-Shiba-Rusinov states would be different in energy. And therefore you change too much in your system. So ideally would be a system where you don't have any charge density wave. And so, for instance, there are other works around where they looked really at the atomic dependence. So both from the Wiesendanger group, but the Parkin group as well. So where they really looked at atomic distance scaling. Our system was just not the right one here to do that. But yeah, you're right. that would be the way to go.
Okay, thank you.
Okay. Good. So yeah, basically, well, I just have to say that we didn't find the signatures, which could have many reasons. I mean, every system is, of course, different. So there are other systems that do show signatures of the 0 energy state at the very end and have been interpreted, of course, as Majorana states, but that's not necessarily the case in every system that you find. So this phase diagram is very tricky. Also, these are quantum spins, so you know, there are many things and excitations happening. So just our system was is the one that doesn't show it, at least, yeah, for these lengths. So I don't know how much time I have. Because I could talk a bit about these Josephson junctions, or there could be more questions. I don't know what you prefer.
I would prefer maybe we will finish the talk and then offer people to ask questions.
Okay, good. But thanks for the questions in between. I think that makes it also nicer. Okay, so as I said, I mean, now you have a superconductor, you have magnetic atoms on top, and what you would think of is, okay, if you take a superconducting tip, so far to us, it was like a tool to increase our energy resolution, to have this sharp density of states. But I mean, you could ask like the next question, okay, why don't you just contact your atom with the STM tip and you have a Josephson junction? And yes, we did that, but we saw some behavior that is now in the literature kind of fancy, that is diode behavior in Josephson junctions. And I mean, diode behavior, okay, is something you know from a p-n junction in semiconductors. I mean, the characteristics that they take to give this word also to Josephson junctions is that basically there's just a so-called non-reciprocal behavior. So, I mean, in the diode, you have this forward direction where you have a current and the reverse direction where you kind of block the current. So this is the characteristics that I take as diode behavior, what is called non-reciprocal. So it really depends on which bias direction you go. And the question is, can you get something like that in superconductors? And as I said, there had been kind of a hype going on recently. And the idea is, so therefore I show this phase diagram that I was introducing at the very beginning. Like ideally, what you could think of, okay, if you have now a biasing as a current, not as a voltage, but as a current, then apparently at some point you get to a critical current density. So where you go from the, let's say, the superconducting state to the normal resistive state. So if you tune your current, maybe you could control this. And ideally now, how you want to get a diode? Well, the diode would be like, imagine that you have a supercurrent in one direction, while in the other direction, you have an ohmic current if you bias with exactly the same current density. So this is what has triggered the field, how to create these junctions, because then, I mean, your rectification ratio would be huge, right? In one, you have zero resistance in one direction, in the other one you have, or in one you have a voltage drop, in the other one you don't have at all. So this is kind of intriguing, and that is kind of what boosted the interest in the field. All right, so there have been realizations in layered structures. If I have time, I would just briefly compare to them at the very end. But since we are already dealing with single atoms in an STM junction, you know, this is what we want to look at. And the question is, okay, do we get this diode behavior? I do change, by the way, the material. You would see that it will be lead and a lead tip and a lead substrate, and then we put magnetic atoms on top. So we go away from this niobium diselenide, but that's for now a minor detail. You can already see this here, that it's a lead-lead junction in the sense like, okay, so we have these two superconductors that when we change the bias voltage, we measure the conductance, then there's these two gaps facing each other. So you have this zero conductance for a wide range. And then you see these BCS like coherence peaks, and now they are really just one peak and not like this complicated structure as in niobium diselenide. So this is our typical tunnel junction. So which means that we are tunneling basically with single electrons or quasi-particles, and you can only do it when you overcome this gap energy. Now, if you come very close with the STM tip, now this is the Josephson regime, and you see, okay, here, so this is again the differential conductance, here the BCS coherence peak, but in between there's something going on. And the most pronounced thing is, of course, this zero bias conductance, and this is typically referred to as the Josephson peak. I mean, it's voltage bias, so you have to be careful with the wording, but essentially, so you have your two density of states facing each other, zero bias, but you can have a conduction. And then you can have also these peaks, and these are called Andreev reflections. So imagine that you want to inject an electron here from the left to the right. I mean, here's no density of states, so it needs to be reflected. It's reflected as a whole, and by that you transfer a Cooper pair. And so this is the first Andreev reflection, and then you can get higher order processes, and this gives rise to these additional peaks. So something like this is very well understood also for STM junctions. I mean, what is a Josephson junction? So here just a lead, plain lead Josephson junction. Now there's one thing that is kind of bothering people that are in superconductivity is the following. I mean, yes, you do have now your junction, you can come very close, But if you look into the Josephson equations, you have a basically the superconductor current is given by some critical current, but then there's this phase difference, right? And this phase difference, or whenever you have a voltage, you already change this phase difference across the junction. So basically, I mean, all these superconducting properties in this phase, they get lost when you do a voltage bias because you immediately change the phase. So for that, you don't want to do voltage bias, you want to do current bias, and then you can have access to these quasi-particle dynamics of this phase. And well, a very simple trick is, okay, just put a large resistor into your biasing line, then effectively you should have a current bias. So it's a very simple trick. And I would also like to really highlight it's an effective current bias. Obviously, it may not be perfect. So if you want to discuss that, then it's there. But the proof is that it's sufficiently good is, okay, now what we measure is we do push a current through that we control. So we call this a biasing current. This is now on the x-axis, while we measure the voltage across the junction. So now this is kind of reverse. Usually you change the voltage and measure the current. Now we change the current and measure the voltage drop. Okay, and in a lead-lead junction, this is a typical spectrum that we get. So imagine we start at zero biasing current. Now we increase the current. We can do that. So here we are in the kind of superconducting regime. There's almost no voltage drop. I will come to the small one later. But suddenly there's a huge voltage drop. So this marks a transition. I mean, once you get a voltage drop, means that you have resistance. So this is why we call it the switching current from the superconducting state to the resistive state. If you now bias it back, you get a huge hysteresis, and then eventually you go back to the superconducting state at what we call the retrapping current. And then you go back to the other direction of your diagram. So you put the biasing current in the opposite direction, you get a switching current suddenly, and again, you have some hysteresis, you go back. So the fact that you see switching and retrapping current tells you that your current bias is there. Otherwise, you would not. I mean, if it was voltage bias, you would just never see this hysteretic behavior and these sharp transitions. Okay. So, I mean, these junctions are then also, I mean, they are well understood in literature, right? I mean, and so basically what you could think of is, okay, you have your tip and the substrate. So you want to have your super conducting junction, and this is what we are most interested in. But then, of course, there's the residual quasi-particle tunneling. So this is an ohmic resistor kind of in parallel to mimic the quasi-particle conductance. But you also have, it's a tip in front of your surface. So there's also some capacitance. And obviously, there's also noise. So this is kind of the equivalent circuit diagram of what we really have in the STM junction, even though we just place a tip in front of the surface. And if you want to do that, I mean, you basically consider all the currents that flow through the junction. So you have then these parallel lines. So you have here the supercurrent through the junction, which I plot here from the Josephson relation. You have the ohmic conductance for the quasi-particle tunneling that goes through this branch. You have the displacement current because you have a capacitor, and you have current fluctuations due to noise that is in the junction. And all these together, they give you your complete current that you actually want to push through the junction. Now you make use of the Josephson relations, and then you get basically an equation of motion in this phase. And this is this phase quasi-particle that we want to look at. All right, now what does it really mean? In terms of what I was showing you before in the sketch. So usually what is to visualize what is happening here in this equation of motion, people take this so-called washboard potential, and then they place this quasi-particle, this phase quasi-particle somewhere. And so if you have zero biasing current, then you're sitting in the diagram here, zero biasing current, but also your phase particle somehow sits somewhere in this sinusoidal potential. If you start to put a biasing current, you actually tilt it. And I mean, if you tilt it, your quasi-particle could still stay here, of course, so nothing happens. But then if you make the tilt sufficiently strong, then of course, at some point, your quasi-particle runs out of the state. And once it runs out of the state, now you get a voltage drop. And now this becomes this resistive part of the junction. And it kind of behaves like a normal conductor from here on. Okay, so then we have switched, and I mean, now if we go back, I mean, because this particle runs already, basically it can still overcome the next maximum because it had the kinetic energy sufficient to overcome the next barrier. So therefore, you see hysteresis in order to trap it back and to get the particle here. All right, but also, I mean, now it doesn't matter in which direction you tilt. Okay, that's fine. But also then I was mentioning there's this small voltage drop that you see here. There's a small slope. So let's say that we have some kind of a biasing current already applied. Well, because we are at finite temperature, there is thermal activation. So eventually this phase particle may overcome one of these maximum. I mean, then you could say, okay, but then it should just run forever because you've once overcome it. And if the particle comes from here, then it has sufficient energy to overcome the next barrier. But there's also, of course, friction. And this friction makes you retrap the phase particle. And this is very important that you have, and what has been called frequency-dependent damping. Only by that you can explain that you have a small voltage drop and before you get to the switching current. So basically what you should do is put another frequency-dependent circuit here for the damping to fully explain this. And this has been found by Kautz and Martinez already years back. Okay, so you see that apparently this, I show you one graph, but I mean, now this seems to be a statistical process, right? I mean, your quasi-particle jumps in and it also needs to be retrapped and so on. So you better do statistics. So we vary the biasing current all the time, and we take many of these spectra, and then we extract the switching current and the retrapping current and get these histograms. And importantly, I mean, there is obviously some statistical fluctuation that's intrinsic to the physics. But if you look into the two biasing directions on a lead-lead junction, it's independent of whether you bias the current to the left or to the right. It's the same both for the switching and the retrapping current. Okay, so this is something that basically has been understood for decades, now just in an STM. But the idea is now, okay, let's put magnetic adatoms, and these give rise to Yu-Shiba-Rusinov states. And the question is, do they affect it? Okay, and surprisingly, so we can measure on both chromium and manganese. And what you see is, so this is the lead-lead junction. If we measure on chromium, you see, first of all, the switching current is reduced. Okay, that's fine. That's probably something that you expect from a magnetic atom. But then what was the most surprising to us is that, okay, if you look into the retrapping current, so it is at a certain voltage, at a certain threshold here. But if you go to the other direction, it's at a very different value, while the switching current is almost symmetric. And if you look into a manganese atom, you also find this behavior, but now, so the switching current is again almost symmetric, but now the retrapping current is also asymmetric. It's different in the two biasing directions, but with the opposite asymmetry than for chromium. And so basically this asymmetry is what we call this non-reciprocal behavior, or what people have thought about diode effect. And now we want to reconcile this to the magnetic properties, or let's say to the Yu-Shiba-Rusinov properties. So I jumped one step, and of course, first of all, I have to show you that these atoms do show Yu-Shiba-Rusinov states. And so we go back to voltage bias, because this is the most clear way to see it, and like we did it also on niobium diselenide. So in gray is again the background spectrum, lead junction, and then we have on the magnetic atoms, we see again different states. And this is true for chromium, but it's also true for manganese. So you really see nicely these peaks here. So these are Yu-Shiba-Rusinov states. And now let me come to this important observation that, look here at this alpha state, we call it. It has a huge electron-hole asymmetry. Okay, so here, and it's in this direction, while here you see an asymmetry which is in the opposite direction. Okay, so somehow, I mean, if you think about it, okay, there's Yu-Shiba-Rusinov states involved. They show electron-hole asymmetry, which means it's also different biasing directions. So at first sight, we always thought, okay, this must have to do with these things that we see also in the retrapping current. And somehow, obviously, this broken electron-hole symmetry may be the reason for having a junction or a non-reciprocal behavior in the retrapping. Obviously, this is when you're far away with your STM tip, but also if you go close and come into this Josephson regime and you see it in the voltage bias. So in the gray, you see this Josephson peak. You also, of course, see it on the atom. But again, here you also see asymmetric behavior here in these lines, which is due to the fact that, of course, I mean, now you have all these reflections and transport processes that go through asymmetric Yu-Shiba-Rusinov states. Yeah. So for instance, I mean, here the first, it's a resonant and rare reflection. So you try to inject an electron from the right to the left, it's reflected. And obviously it now probes the height, so the electron hole asymmetry of this Yu-Shiba-Rusinov state. Okay, it also means, I mean, basically you have an excitation by quasi-particles, and this gives rise to dissipation. The retrapping current is the current which you want to retrap the particle that was already previously running freely. Just by friction, you actually trap it back. So by that, it seems to be already logic that these Yu-Shiba-Rusinov states, which now carry a quasi-particle current being associated to dissipation, that they actually are responsible for the difference in the retrapping current. And this is where Felix von Oppen and Jakob Steiner and Larissa Melischek came in, and they said they just took our experimental data in the current bias, in the voltage bias, how the asymmetry in the current actually is, and they put it into this RCSJ model, so this resistively and capacitily shunted Josephson junction, you know, with this equivalent circuit diagram that I was showing you. And I mean, just extracting the current, so this asymmetry from manganese and chromium, it essentially tells you that you don't have only quasi-particles like an ohmic resistor, but it's a highly nonlinear resistor in there, which has dissipation, of course. And if you take that and you simulate it, you exactly get out these states. So here you have the retrapping, the switching and the retrapping currents, and they see also this asymmetry for the manganese and the chromium just from the extracted current voltages, current values. Okay, so and by this you can then explain, yes, it's really just the broken electron hole asymmetry that we see in these Yu-Shiba-Rusinov states. Those are the ones that give rise to dissipation, and therefore you change the retrapping current, and since they are different and positive and negative bias, this is what gives rise to the non-reciprocity in the retrapping current. Okay, I think I'm really running out of time. I was just going to say that, I mean, there have been these other junctions of superconducting junctions where they have seen differences, but never in the retrapping current. So they always saw it in the switching current. And there, it was not particle hole breaking, but it was time reversal symmetry breaking. And that is distinct to all these prior works on other Josephson junctions that show diode behavior. So with this, let me summarize and conclude. So I hope I convinced you that single atoms are a nice playground to see. First of all, you see these Yu-Shiba-Rusinov states. You can see hybridization. You can play with them. Obviously, you can play with many other symmetries. You can have band formation. But eventually, you can also use these atoms to, you know, make Josephson junctions and see interesting behavior, hopefully. And with that, I would like to thank again all the people who did the work, and thank you for your attention.
Okay, perfect, beautiful. Let's thank you, Katharina, and welcome for questions. Please just go ahead.
Hello. Oh, sorry. I can ask one question. Is so for the Josephson junction, is that possible? For example, for the tip, you use a traditional single element superconductor, and for the sample, we use, for example, iron-based superconductor. Is that possible?
Okay, I'm not 100% familiar with these iron-based superconductors, how easy it is to pick them up and get still the superconducting properties at the tip. So in principle, if you have an elemental one, you can really cover your tip with the same material, and then you have, of course, it's not the single crystalline structure, but you have some amorphous structure on the tip. If you want to now, since the crystal structure plays a role for these other materials, it may be more difficult to get a nice kind of crystallite or flake on the tip that makes you these properties. I mean, in principle, it could be possible, yes.
Yeah. Well, what that means is that for the tip, we use single element metal superconductor, but for the sample, we use different sample.
For the sample, you can use anything you like. Yes.
So in this case, for the experiment of Josephson junction, what kind of signal we can expect?
Okay, so that's an interesting question. So these iron-based superconductors are, of course, also discussed in terms of whether you already have topological surface states and what you can expect there. So I know that people have look then at impurities and so on. Also maybe that there's already at small defects or magnetic atoms that you get topological behavior. If you now come with an STM tip and make a Josephson junction, I have to think more deeply of what happens. Probably I can't give you the answer. One should do the experiment.
Yes, since when we talk about Josephson junction, we just ignore the detailed superconducting properties. We just say it's a superconductor. So, yeah.
I mean, but I think it's already interesting if you take superconductors, which are having different shapes, for instance, of your superconducting energy gap. So not an S-wave superconductor, but let's say a D-wave superconductor. Then, of course, your junction already, because you can scatter, you have to consider whether your Cooper pair tunneling is actually affected by this symmetry of the order parameter.
Selection, yeah.
And there, I think, have been some theory papers that discuss that, and that you should see different signatures because you scatter in different directions. But I have to say that if you really refer to the iron-based, I'm not sufficiently familiar to say what the gap structure and even the superconducting properties themselves are, right? I just don't know enough. I'm sorry.
Thank you.
The first hand was by Matt. Matt, please just unmute yourself.
Hi, thanks for the great talk. I noticed that there was, I saw peaks inside of the tip gap. Do you know what is going on there? Is that like a Josephson current or something?
Yeah, thanks for the question. I was omitting it basically. So it's because we measure at finite temperature. So essentially you see thermal excitations of these peaks. So I don't know if I have a sketch that I can easily show you, but so you already see them here inside, right?
Yeah.
Probably, I mean, the more intense they are and the more close in energy you are, the more you see them. Okay, let me try to explain this. So you have your two gaps, and now you have states inside the gap. And so first of all, you need to excite them, of course, directly. But if, for instance, you have some thermal occupations already, then you see them also at the energy that is mirrored around the Fermi energy. So you should actually see this alpha state that you see here is a thermal replica of the alpha state that's here outside. So you see it on the opposite bias voltage, and you see it exactly at the energy. I mean, so from the gray area to what you have, the gray plus the energy is now on the other side, the gray minus this energy. It's a thermal excitation. It doesn't have to do with the Josephson.
Okay, thank you.
And you can simulate that the intensities fit very well. And I haven't shown this here. I mean, here you see it really nicely, right? You see these very pronounced peak in the gap where you shouldn't see that. But the energy is always, symmetric. And you can change the temperature and see that these change, and you can see that.
Great, thank you.
Augustine, please just go ahead.
Yes. Hi, Katharina.
Hey.
Nice. Very nice talk again, as always. Good to see you. Just a quick question regarding the first part of the talk. So you mentioned that there was a magnetic interaction, right, between the atoms. So what's the nature of the interaction? And and second part of the question is, if you created 2D lattice with these atoms with some frustration, could you have effects of magnetic frustration in these 2D lattices?
Okay, yeah, great question. So first of all, I mean, what our suspicion is that it's just substrate-mediated RKKY-like interaction. So we see it because you see only this quantum phase transition. So now I have to go into slightly more detail. So, I mean, you have these magnetic moments, but your Yu-Shiba-Rusinov states, they tell you whether you have attached a quasi-particle or not. So whether basically your magnetic moment is screened or not screened. And if it's screened, you can't have magnetic interaction. But if it's unscreened, then you can have magnetic interaction. And to compensate, basically, I mean, we start with a screened one, but then you can gain energy by magnetic interactions, and therefore you go through this quantum phase transition. Okay, we believe it's substrate mediated because the atoms are sufficiently far away. It can't be direct interaction. And I mean, you have these electrons, and it's known that superconductors can sustain RKKY. So it's basically just a result from what you expect from theory as well as distance dependence. Now, yes, to look into nice and whatever larger structures where you have frustration and any exotic spin structures. So I think that would be very interesting to look at, in particular, for instance, in these triangular structures. We don't have the spin resolution to look at them. Also, I think that they are probably still fluctuating and highly like quantum spins. But ideally, that should happen, that you should have also magnetic interactions and frustration and interesting spin textures within the superconductor. We just haven't seen it yet or couldn't prove it. But it would be a very interesting thing to look at.
Okay, yeah, very nice. Okay, yeah, thanks a lot.
Any other questions? Please just go ahead.
Yeah, I have one. Can you hear me?
Yes.
Thank you very much for your talk. It was, yeah, I really liked it. So I have also a question on the first part of the talk. So if I understood correctly, so in your measurement, in particular on the long chain results, so you told us that, I mean, if I understood correctly, you are pretty confident that in your experiment, you don't have any signature of this zero energy state or of this Majorana state. And I guess you mentioned that, okay, they were predicted by theory, and maybe they have been also observed in other kind of experiments. So I guess my question is, do you have an explanation of the origin of this discrepancy between your experiment and the theory prediction or other experiments? Or do you understand why you don't have this state, this zero energy state at the edge is here? Or
Yeah, I mean, I can't give a very definite answer. So, I mean, so in the sense of, I mean, we have certain ingredients that are fulfilled from the theoretical prediction. So these bands, they do cross the Fermi energy, and we just don't see the opening of the gap. Now, but if you look closely into phase diagrams, even though you have bands crossing, and maybe this also refers to kind of what Agustin was asking. I mean, that also now, if you take into account all the magnetic interactions that could be there, and so the phase diagram where you find topological phase can be actually reduced to when you just take classical spins. So the original idea was kind of you take a classical spin. So classical spin meaning that you kind of approximate S is going to infinity and you don't have this internal like Kondo-like fluctuations that are there. And then you get a phase diagram and then you say, okay, you should get this opening of the topological gap. If you take quantum spins, so where you have all this freedom of the fluctuations and so on, then the phase diagram where you should find the topological state is already significantly reduced. So that could be an explanation to why, let's say, if you, depending on the theoretical model, if you go really to the quantum model, you should find that, you know, your tunability is much smaller of where you find the topological phase. Compared to other experiments, I would say, because now it's so tricky to get whatever these interactions are, a different material is already something that can be very, very different, I would say. So then your quantum spin nature may be dominant or not. So for instance, in the Wiesendanger experiments, I mean, so with they have built chains and they have seen all these nice band formation as well. But then they, in some part of the chains, they also haven't seen it. In some parts they have, depending on how this hybridization worked. But all of their experiments were explainable with the classical spin model. So maybe then it was like their systems were easier to be in this classical phase diagram, like to see it or not to see it. I mean, it's a tentative explanation, but there are excuses that are reasonable why different systems show different things and why it's a discrepancy to the classical spin model of the topological phases.
yeah, okay. So the original prediction was for classical spins, and now if you have quantum spin, maybe you have fluctuations, and well, okay, I guess maybe intuitively I can understand that it's more complicated. Yeah. Okay.
Yeah.
Okay. Thank you.
Thank you.
Any other question? Actually, have continuation to this question raised by Olivier. If spins are close to classical, could you think about magnets in these chains, and if these magnets propagate around, would be a good picture? Or
yeah, I think it would be a good picture. So, I mean, in other chain systems, not on superconductors, people have tried to see magnons by how they excite inelastic spin excitations, and they have been seeing it, that there should be magnons. I think there should be an analog exactly also on the YSR states. It's okay. I mean, I advertised it as a big advantage that we have these states inside the gap and you get better energy resolution. But also you should now say that, okay, but then also your energy scales that you can look at are much smaller. So now obviously you need to buy the excitation coupled to magnons and therefore see magnon excitations now in an energy scale that is again very narrow. So maybe it's not as easy as it sounds like, but I think that they should be there. There should be some magnon excitations. The question is how to see them in the experiment. Yeah.
Okay, thank you. Do we have any other questions? Please just go ahead. Just unmute yourself and ask. Let's wait 10 seconds. Okay, if not, let's thank you the speaker again.
Well, thank you, Dimitri.
Thank you for fantastic talk.
Thanks, Dimitri, and the whole audience for listening and inviting me. It was a pleasure.
Yeah, thank you. So bye everyone, and see you in a month.